We have been looking at resonance in a parallel RLC circuit. Let's look at the dual of that. We'll look at resonance in a series RLC circuit. A series RLC circuit is also an ideal model. It's a model of an ideal capacitor. We don't model the parallel resistance across it, that first order model of loss in a capacitor, but we can model the series resistance associated with the inductor. This series resistance can be that associated with inductor as well as that associated with our ideal voltage source. So again, we'll look at this instead of developing it from the beginning. We'll look at it for what we know about parallel RLC, and we will use our concept of duality. So whereas in a parallel RLC, we summed up the admittances to find the input admittance of a driven current source, here we'll sum up the impedances of the three elements to find the input impedance from the perspective of a voltage source. So again, our impedance as a function of S, using the impedance for our inductor as SL, the impedance for a capacitor is 1 over SC. And then substituting in for S is equal to j omega, since again resonance is a sinusoidal steady state phenomena. So we plug in for S omega, and we pull out the imaginary j component. We see we have j times omega L minus 1 over omega C. So at resonance, the circuit is completely resistive, just like at resonance in a parallel RLC, the circuit is completely conductive. Our omega naught is still equal to 1 over square root of LC. That's what makes this go to 0. If omega is equal to 1 over square root of LC, the imaginary part goes to 0, and the series resonant frequency is found to be the same as that of a parallel resonant frequency, just as we found when we were looking at transient responses of series and parallel RLC circuits. If we try to use our duality factor to continue to analyze these, or duality concept, what we had for our parallel RLC, we drove the parallel RLC with a current source. If we drove it with Im cosine omega naught t, then that voltage across all the elements at resonance was just that amplitude Im times R. And again, that's our voltage phasor. To convert that to a phasor, we don't have any phase shift difference. The voltage and current are in phase. So the dual of that is that we drive our voltage source here, Vm cosine omega naught t. The current through all of the elements will be the Vm over R, the dual of V I, the dual of R, 1 over R. And again, that's our current at resonance. We will be in phase with our voltage source. If we take a further look and we try to analyze the quality factor, well, our quality factor, the definition of that was the sum of the energy, or all of the energy stored in the circuit, divided by the power loss in the circuit times the period of our periodic function that's driving our resonance. So for our parallel RLC, we had 1/2 that our energy in the inductor was equal to 1/2 C R squared Im squared sine squared omega naught t. Well, that's supposed to be our 1/2 L IL squared. We see we have the C here. We got that by substituting when we took the current through the inductor. We had to integrate our voltage, which was I times R, and we brought out the omega naught and we substituted. So that's how we got it into this form. So you can review that. You can do the same thing here if you want. This is just going to be our 1/2 L I squared, where our I is Vm over R. So our Vm over R squared, we get the 1/2 L and our cosine squared. And you can show that they're the dual of each other. The dual of L is C, the dual of R is 1 over R, and the dual of our sine is our cosine, and dual of Vm is Im. I don't know if I said that. So similarly, we can do the same for our capacitor and energy stored in the capacitor. We take the dual, the power lost in the resistor is our Vm squared over R, 1/2 that, since we're not using RMS values, and then we got our 1 over F naught for the period, so that's the same, and we see that they're both the dual of each other. Our quality factor, of course, is the sum of the energy, or all of the energy, divided by the power, and we see when we sum these two, they both have the same coefficient, and our sine squared plus cosine squared was equal to 1, so we just have the sum of these, so we remove the 1/2 factor, we have LVM squared over R squared divided by this term here, and that's going to give us our quality factor, similarly what we did with the parallel RLC, and it should turn out to be the dual of that. So when we go ahead and do that, well, also we have to multiply by 2 pi to get it in radians, so we get our 2 pi times F naught L over R, or omega naught L over R, which is the dual of omega naught RC, right? For our parallel, we found omega naught RC, so we have the dual of that. So if we remember one, we can get to the other. And again, we can also state our quality factor as 1 over R square root of L over C, again the dual of this form of the quality factor. And then the form of our quality factor for parallel was resistance in the circuit divided by the magnitude of either reactance, either the capacitive reactance or the inductive reactance would give us the quality factor. They'd be equal to each other, and similarly we have the dual of that, so that's in a series RLC, it's the magnitude of the reactance divided by the resistance. So that's our quality factor for a series in RLC circuit, comparing it to the parallel and it being the dual. If we look also at our half power bandwidth and our half power frequencies and the number of half bandwidths off resonance and the resonant frequencies, all of these aren't particular to any type of resonance, so those formulas remain the same no matter what type of resonance we're looking at. The approximate impedance for high Q series circuit is the dual of the approximate admittance for a parallel RLC circuit. If we look at those approximations, so our impedance at j omega is approximately equal to R times our 1 plus Jn, where n is the number of half bandwidths off resonance. So that is the dual of the admittance. If you recall, for our parallel RLC, our admittance, our Y of j omega, that was approximately equal to 1 over R, 1 plus Jn. So we only taken the dual of the resistance. We don't take the dual. Remember, there's no dual for the half power bandwidths. They're the same for both series and parallel RLC circuits. So that's our impedance. If we want to take just the magnitude of the impedance, we can get that's equal to R times the square root of 1 plus n squared. The angle of the impedance isn't, the resistance doesn't come into play there. We just get, it's the our imaginary part, tan inverse of n divided by 1, or tan inverse of n. All right, so that's it for this video. The next video we'll look at an example.